I have the pleasure of introducing Rafael Damian Wolicki. He's a professional chemist working in technical sales and business development at Centris, where he supports the commercial development and technical positioning of new solutions in the energy sector, applied mostly to hydrocarbons and new vectors. He holds a PhD in chemistry applied to energy transition with a focus on catalyst design and catalytic reaction modeling, CO2 conversion into synthetic fuels, and technologies for hydrogen production and storage. During his academic career, he gained experience in the study of chemical processes related to the energy transition and emissions reduction. In his current role, he combines technical expertise with business-oriented activities, contributing to the interface between technology development and industrial applications. Thanks to the experience gathered both from technical and the commercial side, his work is positioned within the broader context of energy innovation and sustainable solutions applied.
So, good afternoon to everybody. Buonasera. It's a very great pleasure for me to present a couple of slides. I hope it will not be too boring for you guys. I know that we have plenty of engineers here. I'm a chemist, so I'm going to go a little bit more in the depth of what's going on in terms of hydrogen interacting with metals, with materials. It's actually quite interesting because once you start learning about what's going on inside the metal lattice and what's going on with hydrogen going inside of it, it's slightly touches something that we don't like to talk about in chemistry. I'm going very shortly into that, but just to don't spoil anything to you. So, probably as most of you are aware, hydrogen is the new challenge of our era. Right now, we are very prone to invest in hydrogen. We want very bad to make it work, but the challenges that the gas poses to us are still there. We didn't find one universal solution for hydrogen to work with what we have right now on the ground. So in the infrastructure that we use for gas need to be adapted, need to be upgraded, let's say. And some of the challenges that might actually be the most disturbing is that hydrogen doesn't work very well with metals. Just a small insight, last time I was checking the tables provided by the lawmakers, most of the metals are considered at best not very susceptible to embrittlement. There's no metals today that are immune to embrittlement, which means that we have still some, let's say, some work to do. It's still a very big challenge. The biggest problems, of course, for the hydrogen in this context is the broad range of corrosions. What we call corrosion here, it's just a word. The mechanism behind the corrosion is very complex. Right now, there are still some theories that are going to crash between each other because the team is still evolving. It's still something that we need to figure out somehow. And it poses a lot of challenges. That's probably one of the biggest challenges in terms of broad use of hydrogen in today's energy mix. After that, we have also some challenges in terms of electrochemical charging. This is a consequence of what we got from how we produce hydrogen, mostly. And of course, the high pressure of hydrogen is mostly related to its chemophysical characteristics. Okay, it's a very light gas, low density, a lot of energy in terms of mass, but not this much in terms of volume. This is a very big problem, and we try to mitigate that by going up with the pressure. Of course, this poses a lot of issues, a lot of challenges. It needs a lot of attention that most of the substances we use right now doesn't require us to actually adapt. What you can see here, it's a very interesting image because there are 6 different theories of how hydrogen interacts with metal. They are not there because they are theories that are separated. from my point of view and what I actually found in the academic literature right now, some of those mechanisms are actually correct. So there are 1, 2, 3, 4, 5 different mechanisms that might actually coexist. And the biggest problem is that the mechanisms of how hydrogen gets inside the metal right now are split in 2 big categories. The first one is that they can go inside during the fabrication. So whenever you're producing any kind of metal, in some situations during the thermal treatment of the metal, there might be, of course, it's not something that you want, but it might actually occur that hydrogen gets inside the metal during the production. And this lowers the mechanical resistance of the material. Okay, this characteristic by itself, it's something that decreases drastically the mechanical ductility of the metal and makes it something that you don't want to put on high pressure vessels and something like that. After that, lately we also started to notice that during the service of any kind of metallic vessel, you're having a lot of interaction between hydrogen and between the metal. And this is mostly cases, in this case, by high pressure, and in this case, by a switch in temperature. It can occur at low temperatures and high temperatures. That you have different mechanisms, different manifestations of the interaction between hydrogen and metal. But anyway, you can notice that hydrogen tends to concentrate in some small areas inside metal, and it tends to create cavities. Those cavities are what makes metal brittle, let's say. It's not the best term to say right now, because in this case, what happens is that metal loses a part of its structure, and the more you go inside of that, the less metallic the structure actually becomes. Right now, we can say that there are 4 main mechanisms about how hydrogen gets inside metal and how hydrogen causes any kind of damage to the metal. This is very important because you're going to see that most of them might look that they are similar. Okay, there are some similarities between each other, but in terms of the effects. But what changes is the evolution of the mechanism, because the evolution in this case, whenever you're having an interaction between gas and metal, changes drastically the usability of specific material in specific applications. So, going straight into it, the biggest problem that we heard probably the most about is the hydrogen embrittlement. Okay, so the sometimes reversible, sometimes irreversible loss of mechanical structure of metal. There are 6 different possible mechanisms. Some of them were actually observed, some of them are just theories, and like I want to say, the math is there, so it just works because the calculations are on point. One of the easiest and one of the oldest theories is that the embrittlement might actually occur because of the high pressure of hydrogen. So basically what you can see on the image here is that hydrogen starts to penetrate inside the metal. The funny part is that for us chemists, speaking about hydrogen as a molecule is fine. Here we are speaking about atomic hydrogen. Atomic hydrogen by itself, it shouldn't exist, because it's something that combines very easily to form a molecule. Whenever it becomes atomic, you're having a very active species. That activity, it's probably something that interacts very easily with your material and interacts with metals that, in most cases, how we perceive them are something that it's very resisting. But this kind of reactivity of a very active gas on top of the surface combined with high pressure, it's what makes this kind of issue a very big problem, because you cannot escape from that. It's sort of a catalytic reaction where hydrogen gets activated on top of metal. So basically what happens is that hydrogen bonds on top of metal, it splits in two active hydrogen atoms, which penetrates inside the metal, and they start to concentrate, as you can see on the image, on the small cracklings that are naturally inside the metal, and they start to merge. So you're having this kind of what they call fish eye defects, which are what actually causes the failure of the metal after several applications, because here the keyword is that this mechanism is actually something that occurs after several applications. The more you use your metal, the more you use the high and low pressure, the pressurization mechanism, the more you're accentuating this kind of phenomenon. So this is the oldest one, the less elegant one. We don't have a lot of images here. The next one that we're going to observe are actually much nicer. We can speak about that. So here are something that some of those images are actually from my thesis. I actually got those images. Some of them are from the literature, so I'm going just to say which one are mine and which one are not. This isn't mine. Another theory is what they call HIPT, so hydrogen-induced phase transformation theory, and this is a particular mechanism that is binded to only some kinds of metals. In this case, in zirconia, niobium, vanadium, and thallium. Those metals, as we say in catalytical chemistry, those metals are more active, more prone to activate hydrogen and split it to active species and make it reactive on top of the surface. What happens here is that you have 4 different steps. Those steps are actually something that occurs sometimes in a very long time, sometimes it needs split seconds. That's what makes this very, not very dangerous, but very unpredictable. And we need to keep an eye on that. The first phase is what we saw before, is the diffusion. So you still need a diffusion of gas inside the metal to get the above said mechanisms. After that, you're having the hydrate growth. I would say it's hydrate formation. Hydrates are a category of molecules where you have metal and hydrogen combining together. And what actually happens is that it turns a little bit to a kind of powder. Okay, so the metallic structure, the shiny, very strong, very resistant structure is not there anymore. You're getting something similar to sand, clay, let's say. And this characteristic is actually what makes the crack. After you lose the structure, you lose the resistivity, the crack starts, and once it started, it stops at some point. That's the diffusion of the mechanism. So you have the interaction, formation of a new molecule, the crack formation, and once it's done, you're done. There's no turning back from that point. Here we don't have any kind of photos because this is still a theory, but it's very similar to what we saw in the first mechanism and in the second mechanism. It's more or less a combination. HEDE is a hydrogen-enhanced decohesion mechanism. So basically, hydrogen penetrates to the lattice of the metal, inserts itself inside the cracks, and once it starts to interact with the metal, it kind of forces the metal to decohese from each other. So you're starting to having like it's more similar to the typical corrosion mechanism, like we intended in chemistry. So you're having a detachment of 2 pieces because you're having a strong interaction between hydrogen and one of them instead of the interaction between the 2 sides of the metal. This is something that still remains in theory because it's very hard to observe this kind of phenomena. It's either more inside the reaction mechanism, and the fun part is that this kind of mechanism is somehow observable indirectly during the TEM image analysis, which we're going to see very shortly. So here, those on the left are mine. The HELP, so hydrogen enhanced localized plasticity mechanism, is probably the most visually appealing mechanism, and it's something that we observed several times. So basically what you have here is that hydrogen turns to penetrate inside the metal, like we've seen in the previous mechanism, and it induces the plastification of the metal. Basically, the plastification of the metal is whenever you're changing the structure of the lattice, so you're having an insertion of an external atom, external molecule, and it alters the mechanical resistance and chemical cohesion of the material. This is something that we can observe not only for metals, also polymers are very prone to plastification. And what you can see the formation of this kind of bubbles. So those bubbles are spots of localized loss of mechanical resistance and the plastification which occurs locally. This might be caused by a failed production mechanism, or by localized high or low temperature conditions and high pressure of hydrogen. I observed this one on a reactor. It was a low temperature, high pressure reactor, and we observed this kind of small bubbles that form on the surface. Once we did the analysis of terms of mechanical resistance, we saw that the plasticity was much higher than the rest of the reactor. So it was a simple fail on a localized spot. And I think this is the last one in terms of embrittlement. You have the NVC, so the nanovoid coalescence. This is very similar to the first one. So you're having basically the merge of different spots that where hydrogen concentrated inside the metal. It actually starts to merge in bigger voids. Those voids actually causes the failure of the structure of hydrogen. Probably you notice that all those mechanisms, as we started to speak about them, they look like each other. They're very similar one to each other. This is because they were observed on different materials, they're observed on different conditions. So right now we don't have enough information to tell which one of them are actually more right or less right, but the effect that we observed on top of the metal is quite different, because the structure of the metal, depending on the composition, depending on the application, depending on any kind of external behavior that we actually pose the metal on, changes the final structure of the metal once hydrogen started doing the embrittlement on top of it. After that, we observed also some combinations. So, for example, HEDE and HELP synergy, it's something that it's well documented in literature, and right now, once we started using more and more hydrogen in energy mix, this kind of combinational effect, it's something that a lot of academic papers, but also companies are starting to invest to, because they notice that, like we said before, it's not black or white. You need to think and understand that everything that happens on top of your material, on top of metal, impacts strongly how hydrogen is going to interact with it. Okay, let's stick with that. It's probably what makes this subject the hardest to study, because you may never know what happens to your metal if you're not going to destroy it. You just need to do the test, to try it. Once you've done that, you're probably going to figure it out. But it's not 100% sure that once you repeat the same experiment, it's going to give you exactly the same result. It happened to me, it happened to plenty of people around the world. We still need to figure out why hydrogen behaves like it's behaving. Okay, because somebody says that it's very similar to H2S. Completely wrong. It's a completely different beast. H2S is a little bit more predictive compared to hydrogen, because hydrogen has a lot of issues that H2S doesn't have because of their difficult chemical and physical properties. So how can we save ourselves? What's the strategy here? We have the tables. Like I said before, this might be slightly outdated because it's 2018. I heard that they did a last update last year, if I remember correctly. And here's just a short list, okay? What's funny is that there's an extremely embrittled metal, several embrittled metals, slightly and negligibly. There's no not embrittled metal. We cannot save ourselves from that. We need to figure out still how to make metal non-reactive to hydrogen. And in general, something that it's very important is that aluminum alloys are probably what we should head right now into, because they're having some very promising results. It's still a lot of work to do, but it's looking promising. We're having some working space there. After that, we can talk about the hydrogen-induced cracking. I saw some papers when they talked about embrittlement and cracking like they're the same thing. They're not. There are two different mechanisms, there are two different phenomena that cause similar damages, but there's one very big difference that most of people ignore. In some cases, embrittlement can be reversible. In some cases, the cracking isn't reversible. Once it's cracked, it's done. You need to change the piece. And basically, the cracking doesn't occur if there's no external force. So by external force, what do I mean? You're having somebody pushing on top of a piece, or simply you're having high pressure inside a pressurized vessel, which pushes on the walls of a cylinder, of a reactor, whatever you're having. If you're having this kind of factors, you can speak about cracking. Without that, it's impossible. Also, something very important is that for the cracking to occur, you need to have an aqueous medium. It's even enhanced with H2S, which seems from the latest observations to enhance this kind of effect on top of metal, but it's still very profoundly, very deeply studied matter, because liquid combined with hydrogen, and liquid hydrogen is a very hot topic right now. They're giving a lot of money for the studies in that matter. So just keep in mind that those two different mechanisms are, we can also say that the cracking is probably a direct consequence of the embrittlement. So you're having embrittlement, if you're having a lot of conditions that actually matches, you can lead to cracking. No other way around. Blistering, it's something that also starting to get some space, because it's very important for us to understand that several materials, several different pressurized vessels can be susceptible to the interaction on top of the surface, and you're getting this kind of very nice bubbles which forms and makes your metal wavy. Okay, that's basically what you're going to observe. The funny part is that a blister can be actually several meters long. There are some photos on Google, you can look for that. We say that the blisters can go from millimeters to meters in terms of dimension, because it's just a propagation of the nanovoids formation. So having the nanovoids, which we talked before, once they merge and they make the metal bulk, they can form different structures which can merge on top of each other and form this kind of blisters. How do we prevent the formation of this one? This one is actually something that is actually very observable on high pressure vessels. Usually the sulfuric groups on tops of metal, which in most of the cases are just contaminants, acts as nucleation site. So you're having nucleation site which induces the formation of the blisters. We noticed that by desulfuring the metal, we decreased drastically the formation of the blisters. So it's just a matter of working with a specific standard and given that this kind of events actually can lead to the failure of the vessel, it's something very important. So people are starting to get much more sensible also regarding the good manufacturing procedures in terms of formation of not only pipelines but also pressurized vessels. The last one is the hydrogen attack, which is, here we are talking about the proper corrosion. This is the proper corrosion mechanism, and it's only linked to the high temperature hydrogen attack. Okay, it's a degradation, like it was discussed previously in the previous panel. So it's a chemical attack on top of the surface, and you're noticing the typical signs of corrosion. So having the surface decarburization, the internal cavitation, and fissuring, and once you're getting very deeply inside this kind of mechanism, you also start noting some blistering. So the penetration inside the structure and the dilation of the lattice. So you're seeing some very nice bubbles, like you can see on the photo below. So this is probably my last slide. How do we prevent the hydrogen effects on top of metals? The easy answer is we don't, but I think you're not here to actually listen to that. We have some mitigation strategies which can work on medium to long term, but they are not permanent. The first one is the surface coating, the easiest one, probably the most efficient one today in terms of cost savings. Because right now we are also starting to think about repurposing pipelines that we are using for natural gas, for example. Right now they're using it with a mix of hydrogen and natural gas, but they are starting to think to go higher in pressure, higher in percentages. And I saw also some projects when they want to go all in on full hydrogen. If the pipeline is not coated, I would strongly advise to not do that, because hydrogen interacts very easily with metal, like you saw before. And the coating is probably the easiest way to just make it a little bit easier for us. Once you're excluded your coating for any kind of reason, you can work on the surface modification. I don't remember the name of the sir that spoke about the inhibition of hydrogen effect on top of metals, but actually something that we do, the passivation of the surface, for example, it works very, very fine. Not for a long time, it needs to be repeated once in a while, but it's still something that may actually work. It's a strategy for maybe low pressure applications, but still looks applicable. After that, you have the microstructure modification, but here it's a little bit more into the formation of the metal itself, so the production process and so on. And like we said previously, the right material selection. This is the key point. If you're working with aluminum alloys, it's perfect. Anything other than that, it might actually be a very big problem, a very big headache. So just keep it in mind. And for today, we don't have anything else. It might be anticlimactic, I know, I'm sorry for that. But the studies are actually going on, and right now I saw also a very nice application. This is actually a little bit of science fiction, but it might actually be very interesting in a couple of years. I saw some nanoparticle application on top of metal when they basically put some metallic nanoparticles. We are speaking about 15 to 20 nanometers nanoparticles, densely populating the pipeline with a specific production method, and this kind of nanoparticles tend to absorb hydrogen on top of it and doesn't allow to penetrate inside the metal. So you're just making hydrogen adhere on top of a passivating agent, and after that, after you depressurize, it just goes away. It's as simple as that. Might actually work, why not? But for knowing the people that produce pipelines, I don't think they are not going to stick to this production method. It's a little bit costly, but who knows, maybe one day. And you have also some very nice standards. Once again, some of them might be outdated, so please check beforehand going inside that, because there might be some news about that. Okay? So thank you very much. If you have any kind of questions, I try to answer to them. Of course. Consider that any kind of external force that works on top of a metal changes drastically how you notice the hydrogen effect inside its structure. For example, if you're having an embrittled metal, what can happen is that you working with a perfectly safe vessel, you pressurize it, it just fails. Okay, it happened. It will happen. It's something that happens mostly because it's a mechanism that you don't notice up until you open the vessel in the middle and you just crack it open. The hydrogen induced cracking, for example, it's a little bit more gentle because if you're lucky and your vessel is cracked before you start working, it just doesn't increase in pressure. So you notice it in terms of how it behaves once you try to just make it to work. So yeah, absolutely, the manifestation changes drastically.